All right, good afternoon, everyone. So today we're going to finish up this unit on trees and ensembling. Just to remind us where we were last time, we learned about ensembling, which was combining different models, either averaging them or taking something like a vote if they give you discrete outputs, categorical outputs. And we talked about trees, decision trees, as a new way of building predictors. And then we combined those two ideas together here for random forests. And a random forest is a collection of individual trees that on their own, typically when you do this, you make them really simple. So very, maybe the depth is small. You randomize the data that you give to each tree. Maybe you randomize the features that each tree sees. But at the end of the day, you get an ensemble of trees, and then you can average them together and improve their performance. So the key point here is that these trees are trained individually, and then at the end, they're combined. So what we're going to talk about today is a different approach where you train an ensemble of models sequentially. And this is called boosting. So for example, in this picture here, you have a data set. Use this to train your first model. It could be a tree, it doesn't have to be a tree. And then you see where that model has made errors on the training data. So maybe these orange points here are where it made errors. Then, using this knowledge that, okay, I have this model, but it was having trouble with particular training samples, you train a new model. And this new model is trained so that in combination with the previous model, it works pretty well. And then you take this new approach and you see where did it make errors. And then you say, okay, I'm going to train a new model so that when combined with these models, the result works pretty well, and so on and so on. So you sequentially keep training a base model so that it works well with the boosted model, which is this ensembled model of the previously trained ones, ensembled version. So that's what boosting is. So we're going to talk about three different approaches to boosting, starting with a relatively simple one, AdaBoost, and then talk about gradient boosting, and then a modern one, which is extreme gradient boosting, which is very popular in machine learning contests just because it works so well. Okay, so AdaBoost is just the simplest one, so we'll start there. So the predictors, our base models, we're going to use little f for the predictors. We're going to use m to index the stage. So this would be m equals 1, 2, 3. And roughly speaking, what we're going to do is we're going to go sequentially for little m, 1, 2, and so on. Train predictor fm to minimize some weighted loss. So here you have a loss between the training label and the prediction. And then here you have a weight. Notice that this weight depends on the stage m you're at, as well as the index in your training data. So you train the predictor to minimize this weighted loss. Then you evaluate how that predictor worked on your training data, and you set the weights for the next round based on if this previous boosted predictor didn't do as well. You up the weights on those samples. You say, these are more important. We're having trouble with these. Let's focus more on these samples. The final strong learner here, you can see it's a summation of the base learners, but each one is weighted by some weight alpha m. So this is going to be some linear combination of these, gives you the final combined one, and we're going to use a capital F for this boosted or combined model. Okay, so for now, we're going to be, just for simplicity, we're going to focus on binary classifiers where F outputs either 1 or -1. There are other versions of this for regression, for non-binary classification, but we're just going to focus on this simpler case. Okay, yes?
In this case, are you changing the hyperparameters each time in the model, or is it the same hyperparameters for every sequential model?
I'm not sure what you mean by hyperparameters, but for example, let's say that Fm is a tree. So we have to design the whole tree. So the tree is, the pattern of branching as well as the weights or the outputs for each leaf. Does that make sense?
Yeah.
Yeah. I think you could do this with, I think you could probably extend this to linear models and so on too. In that case, you're just, training the linear models. But we'll focus on trees. Okay, any other questions? Okay, so here's the derivation. So we're going to assume that we have our training data, x, y pairs as usual. And not surprisingly, our y's are going to be plus minus 1, which is the same as the classifiers we're designing. Okay, and so we're going to define this step M boosted classifier as the capital F with little m here. So this is at stage M. This is like the cumulative weighted sum of all those individual base predictors. So here you have the previous capital F plus the most recent base predictor times its weight. So you start with F0 equals 0. You'll design F1, alpha 1. That will give you capital F1. And then now you move Fm to 2. This will be your capital F1, which you know. And then you need to design alpha 2, F2. And then you'll get your capital F2. And then you move M to 3. You know this part. This will be alpha 3, F3, and so on. So we're just one by one designing alpha and F, and we're going to assume the alphas are positive. And we are going to use as a loss the exponential loss. So this isn't exactly a loss we've seen before, but it's pretty similar to losses we've seen. But basically, you can see that you want the sign of the capital F to match the sign of Y. So capital F will not necessarily be binary, because even though these guys are binary plus minus 1, they're multiplied by some real number and then added together. But you certainly want that this matches this in sign, because then you have e to a negative number. If they don't match in sign, you'll get e to a positive number, and that's going to be larger. So, so this loss is rewarding F matching yi in sign. Okay, so any questions on the setup? Yes.
Do you have to initialize at 0? Or
Yeah.
can you do like a stochastic, you can't do like a stochastic gradient descent thing where you found an initial good starting point?
So what we're initializing at 0 is this cumulative boosting model. So it's just kind of like saying, we're building up this boosted model. So the first time we start with this. The second time we combine those. The third time we combine these, and so on. And so we're saying like, okay, before we have this, we have nothing. That's what it means to set capital F to 0. Okay. All right. Okay. Any other questions? Okay. So, all right. So let's take a look at how the derivation works. So, if we're at boosting stage M, we take our loss and we plug in for this capital FM. We plug in this expression, and we get this. Then we have an exponential with a sum of two terms in the exponent, which means we can write that as a product of two exponentials. This one times, the rest of the stuff. And when you look at this quantity, remember that when we're at stage m, this is what we had already designed at the previous stage, so we know this. We also know our training labels. So we know all this stuff. Let's just give it a name, WMI. And you can interpret this as a weight for boosting stage m on training sample I. So the thing we need to design, or the things, are this alpha m and then this function, or basically like predictor fm. Okay, so how do we go about doing that? Well, it's just some interesting tricks that people developed. So it goes like this. Remember that yi and fm are both binary. So there's basically two things that can happen. Either they agree in sign, at which point their product becomes 1, or they disagree in sign, at which point their product is -1. So basically this quantity is either going to be e to the power alpha m or e to the power minus alpha m. Okay, so what we can do is we can split the sum into the I for which the label agrees with the predictor output, and in that case, this thing reduces to e minus alpha m. So we can just pull that out of the sum because the sum is over I. The only thing left in the sum then is this WMI. Then we have the rest of the samples. The rest of the samples are where the label did not match the predictor output. And in that case, this quantity becomes e to the positive alpha m. And we can pull that out of the sum because it doesn't depend on I, and then we just have the sum over the rest of the weights. So, okay, this is the first step. Now, what's a little bit inconvenient about this is remember we're going to need to design both alpha and f, and both of these terms contain alpha and f. So one way that we can remove the f from this term is to complete the sum. So go from this partial sum to a sum over the full training samples. In doing that, we had to add in a whole bunch of these samples that obey this. To preserve this equality, we're going to subtract them. So these things are the things we added to this to get this. So here we're subtracting them. What that does is it makes this first term independent of fm, which means when we do the optimization over fm, we can forget about this term. We can focus exclusively on this term. Okay, so is everybody good with that? So we're going to optimize the second term over fm first. We'll deal with the alphas later. The next thing to realize is that this is independent of fm. This is just some scalar, and because alpha is positive, this is going to be larger than this. So this thing will be positive. And so if I'm trying to minimize the loss with respect to fm, I just need to minimize this with respect to fm. I can basically forget about the effect of this for now. Okay? And what is this? If you think about it, so this is the thing we're trying to minimize now. Another way to write it is to write it over this full set of training samples and have an indicator function that equals 1 when they don't agree, or it equals 0 when they do agree. So now you can see this is basically just like whenever there's an error, this turns on, and this is just looking at your weighted, I don't know, it's not exactly an error rate, it's like a weighted total amount of error. So for every sample that's in error, you multiply it by this weight. So if we had a 1 over n, you could call it a weighted error rate, but it's not really a rate because it's missing the 1 over n, but hopefully you can see what this is. So we'll call this a weighted misclassification loss. Okay, so what happens when we design the very first predictor, we'll just set all the weights to 1. So we'll set all the weights to 1. And then basically, at that point, you're just saying, I want to train my first predictor to minimize my error rate. It's a pretty natural thing to do for the first stage. However, the next stage, it's not going to be just minimizing the error rate. You're actually going to be minimizing the error rate, but you'll be weighting the samples where the first stage gave an error on. So those samples will be weighted larger in the next stage. Okay, so that's the idea, and so that's how we train FM. Okay, so so once we know little FM, we have to design the alphas. So it turns out that once you know this little FM, all this is known, and you can design the alphas by taking the gradient of this with respect to alpha m and setting it to 0 and solving for alpha, the thing that we like to do whenever we can. And it turns out if you do that, it's not too hard to show that this is the optimal value of alpha. Here, this epsilon m is this weighted error rate, which is like the sum of the weights in all the cases you made a mistake over the sum of all the weights. Okay, so this is just something we can compute when we know FM, and then once we can compute epsilon m, then we can compute alpha m, and at that point we're ready to move on to the next stage. So in summary, at the very first stage, we initialize all our weights to 1, and then we go through a for loop over m. The first thing we do is we design FM by minimizing this. Once we've trained FM, we can then compute epsilon m, then we can compute alpha m, and then once we know both of these terms, we can add them onto our previous boosted classifier to get this, capital FM, and once we know our capital FM, we can essentially compute the weights for the next stage. And then we repeat the process. So essentially, we just do that until we're done, until we've gone through all our stages. And once we've designed everything, we use capital M as our final boosted model. Okay, so that's how it goes. Let me show you an illustration of this. So here, we have a classifier, AdaBoost classifier. For our base predictor, it's going to be super simple. It's going to be a decision stump. So a decision stump is a decision tree with depth 1. So in other words, it does one split, splits the data in half, and that's it. And it assigns values, to those two outputs. So that's all it does. So in the first, so here's the illustration. So we have a binary classification problem. We have some pluses, we have some minuses. So at the very first round, we need to design our decision stump. So decision stump is going to split the data either horizontally like that or vertically like this. So in this case, the decision stump we design splits it this way. So this would be predicting blue or plus. This would be predicting red or minus. And we can see that these were predicted correctly. These were predicted correctly, but these were in error. So now, for the next stage, we're going to compute weights on all these samples. For all the ones that are correctly predicted, we're going to weight them smaller than 1. So that is represented by the fact that these things got smaller in size and font size. However, these guys, since we made an error on them, we're going to up their weights. So that means next time at this iteration, we're going to pay special attention to those samples, make sure we don't mess up on those. So this time, we have to design another stump, and we ended up designing this stump here. So we split the data again into blue and red, and sure enough, we did fine on those weighted samples. We also did fine on these, but we made errors on these guys here. So now for the next round, we're going to take all these weights, but we'll adjust them. So for example, since we made errors on these, we're going to weight them larger the next round. Because all these were predicted correctly, we're going to decrease their weights, and so they all got smaller. Same with these, got smaller. And for that final round, we have to design one more stump, so we end up designing that one. So you can see our base predictors are very simple. They just split our data in half, essentially. But the final boosted classifier, we're going to multiply each of these by some real numbers, and we are going to sum them up, weighted combination, and then finally take the sign of them, just to get a hard output. If you wanted a soft output, I guess you don't need to take the sign. But basically, this is going to give us this final boosted classifier. And you can see it's perfectly classifying the training data. Even though none of these guys did it perfectly, once we combine them all, even though they're so simple, they're just these stumps, we finally get this correct model here. Okay, and as you can see, this is still a tree. Even though it's like the linear combination of 3 separate trees, we could actually, if we wanted, we could implement this also as a tree, because anytime you have your space split up according to, regions that are parallel with the coordinate axes, there's some tree that implements that. So at the end of the day, in some sense, we have another decision tree. But it's more complicated than just a stump. Okay, so that's AdaBoost. It's just one way to do this. We'll talk about 2 other ways. Any questions on AdaBoost? Okay. All right. So the main limitation of AdaBoost is it's pretty constrained. So remember, we could only deal with binary classification, and we could only deal with predictors that that gave hard outputs. And we were forced to use the exponential loss. It's not really clear how much you can generalize beyond those things. So gradient boosting, that's our goal. We want to do things similar, but more generally, and we're going to have to sort of come up with a new scheme to do that. So as before, our boosted predictor will have this form. That's exactly as before. These are our base predictors, and we'll assume that our base predictors are in some class of models. So for example, perhaps F would be like the set of all decision stumps, or the set of all linear classifiers, things like that. So the F is sort of the model class. So we're going to be designing our base predictor in some model class. And we would like to do this for general model classes, like anything. And then furthermore, we want to minimize this loss. You can see that this part here, L, is general. So we want to be able to handle a general loss, not just that exponential loss. So this should work for regression, should work for binary classification, whatever we have. That's our goal. We saw that we could do this for a specific case with AdaBoost, but we'd like to move beyond that. Okay, so this is ideally, this is what we'd like to do. We want to start out with our first classifier, and we want to train it to minimize the loss on our training data. So this is reasonable. We know how to do this. And once we do that, we'll just, in this case, we'll set alpha 1 equal 1. So we'll just set our first boosted classifier is just our first base classifier. Then we want to go through all the remaining stages, and we are always going to take our previous boosted classifier and add on to it alpha times FM to get our new one. But the alpha and FM that we design, we want to minimize this loss. So look, if you look closely, you say that we're minimizing, so So this is going to be the F capital M xi. So we're designing these things so that when we're adding them onto our previous boosted classifier, that the new boosted classifier after M stages minimizes our loss. Okay, so we're not trying to make alpha M FM on its own good. We're trying to say it's going to work well once I add it to my boosted classifier. So this is what we want to work well. So unfortunately, for most choices of loss, this is just intractable. We can't really do this, don't know how to do this. So that's where gradient boosting comes up. It's an approximation to this that's tractable. And it goes like this. Instead of exactly minimizing, like up here, we're going to settle for a gradient step. So what that means is that our new boosted classifier is going to be our old one minus alpha M times the gradient. Okay, so that's the idea. You know, we should be able to compute the gradient of the loss. But there's a new issue. So remember that this boosted classifier is the alpha weighted sum of the base classifiers, but the base classifiers should be in some model class. If you look here, there's no guarantee that this will be in the model class. It's just the gradient of some loss. So how is that going to end up being a tree, for example, if we're saying I want to design a tree? This may not be a tree. It may not be of this form. So we can't do this exactly. So we have to do another approximation. Okay, so here's what I just said. This is what we want. This is what we have. Notice the discrepancy between this and this, where this needs to be in the model class. This part may not be in the model class. Okay, so the solution to this is don't do the exact gradient descent. Rather, train an F that is in our model class, let's say a tree, that's as close as we can get to this negative gradient. We want to make this as close as possible to this. Okay, so it's not the exact gradient, it's an approximation of the gradient, but that's how we can guarantee that it is in the function class we want, that it is a tree or decision stump or whatever. Okay, so how we do that, we'll just use the quadratic loss, RSS. And just in terms of terminology, let's say that this is the gradient of the loss with respect to the second term. Our loss is operating on y and the prediction. So it's just the gradient of the loss with respect to the prediction, evaluated at the previous boosted classifier. And this is all for a specific sample I. So here we can give this a name. We'll call this thing minus RMI. M refers to the stage of boosting. I refers to the sample in our training set. The reason we're putting a negative sign here is because so that if I put a negative sign here to match this, then this becomes a positive sign. So if I want FM to match the negative gradient, then that means I want FM to match RMI. So that's what we're doing here. FM, when you feed it XI, should be close to RMI, and we're going to assume a quadratic loss. That's how we're going to train it. Okay, so even though we might be doing classification, we're training F as like a regression algorithm. Okay, so now let's say that we've done that. Let's say we've designed our tree, or whatever. Now we still have to figure out how do we design alpha M. So if we come back to what we originally wanted to do, which is to minimize this, where now we've designed FM. This is tractable. This is just alpha M is just a number. We can do that optimization in a straightforward way. In fact, this is just a scalar, so we can do like a line search. We can do a whole grid of different alpha M's, search over the grid, and find the one that minimizes the loss on our training data. Okay, so now we've designed FM and alpha M, and finally we just update the boosted predictor. And we do this for each M. Okay, so that's just to recap. We started with this idea where we want to minimize a general loss L with a boosted predictor like this, but we want that the base predictor is in some family of models, like a tree, like a stump, something like that. We saw that the optimization problem we'd love to solve is too complex, it's intractable. So instead of doing this exact minimization over F, we settle for a gradient step. Even that prevents us from guaranteeing that the update is in the model class. So we do an approximation of the gradient step where we give the gradient values a name, RMI, and we choose, or we design our model to be close to those guys in RSS. And finally, we just choose alpha via line search. So now we've designed alpha M, and FM, and we just add them to our previous boosted predictor to get our next boosted predictor, and we repeat over and over. So, questions on this? I realize there's a lot of math today, so if you're not getting all the details, it's not a problem. Just try to get the big picture. So in practice, people have found that it helps to modify that procedure a little bit. Even though we worked hard to get the exact best value of alpha M, it works better if you slow down these updates a bit. You multiply by some mu. It's kind of like a learning rate in gradient descent. And so by default, sklearn uses mu equals 0.1 for both its gradient boosting classifier and regressor. You could use another value, but that's the default. Another interesting thing is, as the base classifiers, it uses 100 decision tree classifiers at depth 3 for both regression and classification. And yeah, everything is implemented in sklearn. It's just one example. This is a regression problem. It's a one-dimensional regression problem, so this is the feature, single feature X. This is the target Y. The blue curve is the true model. Yeah. Usually we don't know the true model, but this is a synthetic example where someone created a true model. So it was known, we can plot it. Not known by the algorithm, of course. And so what we're going to do is we're going to use, again, decision stumps. So there'll be trees that, the very first one is going to be, it's hard to see, but it's this. Okay, so basically it splits the data, which is just feature data X, basically splits it here. So now we have X less than this, it assigns it one value, and X to the right of this, it designs a different output. So we have two different output values. So that's what the first decision stump does. That was the best thing to do. Then it designs another stump, which it adds to it. And after you design another stump, you get a slightly more complicated. I don't know exactly which one it is. It's a slightly more complicated shape. It's hard to tell. But as you accumulate stages, it gets more and more complicated. So I think the second one is probably here, although I don't know if it's maybe that, and so on and so on. And as you get more stages designed, you get this more and more complicated boosted function. And finally, after it looks like 2,000 of them, they got this this red curve. And as you can see, it's a pretty good approximation to the ground truth, the blue one. Of course, not perfect because the training data was only these single dots. So not much training data. So you expect that it's going to be kind of rough, like, yeah, well, that's what it designed. And I think just for comparison, it had like a regression tree of max depth 1. That's that. And a regression tree of max depth 3. That would be something like this, I think, just as reference points. Okay, so that's gradient boosting. Any questions on that? All right, so just one more to talk about, which is extreme gradient boosting. So basically, this is just an evolution of gradient boosting. It's won many recent machine learning contests. It just works really well. It works really well out of the box. Like, you just run it with its default parameters, and the performance is really good. Now, you can tweak it. I'll talk a little bit more about that later, but just its default performance is usually quite good. It's competitive with neural networks, but they require a lot of hyperparameter tuning, training, all that stuff. So basically, it's relative to gradient boosting. It has a few tricks. Instead of using just a gradient, which is like a first order Taylor series, it actually uses a second order Taylor series. It adds a particular kind of regularization. We're going to talk about these. It also does other things that I'm not going to talk about. It has a sophisticated way to do the tree search, a bunch of parallelization, hardware acceleration tricks. This software is not part of sklearn. It's in its own separate package, but the way it's written, you can use it very much like sklearn, and you can use it with sklearn as if it was just an sklearn function. It works perfectly well. So let's go through the derivation. So similar to gradient boosting, but even a little bit simpler. This is how we're going to do the boosted classifiers. It's the same as what we're doing, but there's no alpha m's. Or you could say the alpha m's are all equal to 1. Okay, so we don't have to worry about that. All right, so what we do, start by designing the first base model to minimize this loss. And the loss is going to be generic. So once we design this, and this is going to be a tree in the case of XGBoost, so we design our tree to minimize the loss. We set the first capital F equal to that little f that we designed, and we go through our for loop over the second stage, third stage, and so on. Similar to gradient boosting. So this is the new boosted predictor is the old one plus the FM that we designed by minimizing this. Here is the loss, and as with gradient boosting, you can see that we're trying to make the new boosted predictor. This is going to be our FMX. We're trying to adjust FM so that the little fm so that the capital FM minimizes this loss. But in addition, now there's a regularization that operates on that little FM. Talk about what that regularization is in a moment. So here's our regularization. Now this, not surprisingly, is too difficult to solve exactly, just like we saw with gradient boosting. So we're not going to do that. And instead of doing the gradient approximation, we're going to do a second order Taylor series approximation. So it's going to look like this. So we say that the loss evaluated at the previous boosted classifier plus this modification, this addition to it, will do the gradient, the Taylor series approximation about this value. So that means that the zeroth order term looks like this. So it ignores this part, the perturbation. Then the first order term is the deviation times the gradient. So here GMI is the gradient of our loss at this previous stage and at sample I. And then here we have the second order part. So this is the quadratic term times the second derivative HMI. So here's the second derivative of the loss with respect to that second term. Okay, so now let's replace this loss with the Taylor series approximation. Since we're designing little fm, we don't have to worry about this term because it does not depend on little fm. We only have to worry about these terms. So here is the new optimization problem. We've taken this, replaced it with this, and we still have the regularization here. So this is how we want to design FM. We want to minimize this thing here. Okay. Now we're going to focus specifically on a decision tree. And let's say there's a maximum of L leaves. So we're going to use this. We talked about this on Monday. So this is Z is the output at leaf L, and Q of X takes X and assigns the leaf L, so that finally we can write the whole decision tree as Z sub QX. Okay, so here's the regularization. The regularization is applied on the output values ZL. So we have basically something like a ridge regression, but it's on the output values. We have a regularization strength lambda there. And then we have another term with a strength gamma that actually is operating on the depth of the tree L. So this is trying to make the tree not get too deep. And this is trying to make the values output by the tree not too large. Okay, so we have to tune those lambda and gamma parameters. Those are the hyperparameters. Okay, but coming back to this optimization, we now know what all these terms mean, and so we can actually do the derivation. So to do this derivation, it's very similar to when we talked on Monday how to design a tree to minimize a generic loss. So what we did is we replaced the sum over the training samples with a double sum. In this case, we said, look at the training samples for which the tree puts it in leaf L, and then sum over the leaves L. That allows us to replace this with ZL. So that's what we have over here. Oh, and we're going to omit the M notation just to make everything look nicer. So the M's are there, but we're not going to write them. Okay, so we have GI as above. This gets replaced with leaf ZL. This gets replaced with ZL squared. And for the regularization, we just take this and we put this over here. Okay, so we have to optimize the output value Z to minimize this. We also have to optimize the tree Q. So we can do this in two stages. The first stage we'll just optimize Z for an arbitrary Q. So to do this, we can notice that there's a linear Z term, there's some quadratic Z terms, and then there's a constant term. So we basically have a quadratic in Z. So that's something we know how to solve. Just let's collect things. So this is for the linear term, this is the weight on it. For the quadratic terms, this is the weight on it. We have one weight from here, and we have another weight from here. So that's the weight on the quadratic term. And then finally, we're going to write this as a sum over lambda so that we can pull this sum out front and have all these terms summed over L. Okay, so now that we have this, it's we can just take the derivative of z, set it to 0, and you find you get this nice solution for ZL. You then plug that expression for ZL back into this, and this whole thing simplifies to give you this expression. So essentially, this is now the loss that we want to use to design our tree. So it looks kind of complicated, but it's the way we approach it is the same way we design trees always. We just do this top-down method. So for example, at the very first stage, we start with our full training data. We call all the training indices S, and we're trying to figure out a way to split this into two subsets, S1 and S2. In order to do that split, we consider all the different features, and we consider for each feature all the different thresholds that we could possibly use. Those are finite. Both of them are finite, so we can just do a search over them. So let's say we do not do any splitting. The total loss is exactly just this quantity here. So this is without any splitting. We just have all the samples in S like this. Now, if we did a splitting, what we're going to find is that we'll have some subset S1 for which we can evaluate this loss. And that subset will just replace these sums over I with S1. In this case, sorry, so this is kind of these two terms. They're identical, they have the same form as this, but the way that they differ is this has I in S, this has I in S1, this has I in S2. Okay, so if we don't do any splitting, this is the loss. If we split it a particular way into a particular S1 and S2, this is our new loss, the sum of those. So what we do is we just consider every feature and every threshold, and we evaluate this for all those combinations, and we find the very best value. And if we notice that that very best split is actually no better than what we had before splitting, we say, we're not going to do any splitting. We're done with this branch of the tree. Let's move up and move to some other branch. However, if we can improve the splitting, we'll do so. We'll do the split, and this will be the new cost. It will have decreased. So in this way, as you build this tree, it sort of automatically adjusts the depth of the tree based on this criteria. And if you look closely, you can see lambda appears twice after a split, but it appears once before a split. So what that means is that, remember, lambda is this term here. Lambda is this term. Lambda is supposed to weight the total depth of the tree. So as lambda gets larger, you should have, weight the number of leaves. As lambda gets larger, you should have fewer leaves. And you can see that here because if lambda doubles and you want this to decrease, the larger lambda is, the less of a chance that this is going to be smaller than this. So that's how it works to regularize the number of leaves, to limit the number of leaves. Okay, so basically that's it for XGBoost. Again, I realize there's a lot of details here, but just to summarize how it works. This is just one example. There's also a demo 10, that has this all coded in Python. But I just wanted to show you here that the way that you deal with XGBoost is exactly the same way that you would deal with any sklearn model. You instantiate it, you do the model.fit, then you do the model.predict, and that's it. So then just a few comments for your projects. These trees tend to work quite well out of the box, but you guys are going to be competing against each other in the project. And part of your score is how well you do in the Kaggle competition. And, you know, it's sort of a zero-sum game. Like, if you just do average, you're not going to get as many points as someone who does better. So just, doing the out-of-the-box tree is not going to score you a lot of points because all your competitors are going to be trying to make it better. So here's a bunch of different links, different articles with different people's recommendations on these are the hyperparameters that matter most. This is the order you should do a search in. If you're going to do one hyperparameter, optimize that, then do another one. You can try to jointly optimize these hyperparameters, but it just takes time. As you know, if you try to jointly, it basically goes exponentially in the number of things you're trying to jointly optimize. So there's a lot of tricks and experience that people have gotten from playing with this, where they've learned these are the things that matter most. Try these first, and that's what these articles describe for random forests and for XGBoost. These are just a few that I thought were pretty decent. There's obviously other articles out there too. You might find one you like even better. One very last comment is you might hear about feature importance is something that when you train a tree, whether it's XGBoost or random forest, sklearn or XGBoost, it gives you just out of the box a rough indication of how important each feature is. And there's different ways to configure it, but that information can be useful for feature selection. The way that it's computed in trees is not exactly what you want for feature selection, but it might work well, it might not. You'll just have to tell with cross-validation. But I just wanted to very quickly describe what's done. So for random forest, it basically the way that features are ranked is what's called mean decrease in impurity, which is essentially how the Gini impurity changes on average when a feature gets split. So remember, Gini impurity was something we talked about as one of the splitting criteria for categorical labels. And it basically says, if you get, for every feature in your data set, it gets split maybe many places in the tree. So you look at all those places in the tree where that feature got split, and you look at how much the Gini impurity improved after a split. And so for features where it's, persistently increasing improving Gini impurity, that should be an important feature. For ones where it's not really changing, that's probably not an important feature. So that's how that feature importance works. But there's sort of a problem with this, that features that are high cardinality, meaning there's a lot of possibilities for the feature, end up giving you, are biased, give you larger values of this MDI. So in other words, if you have a feature with two values, a categorical feature with two values, versus a categorical feature with three values, the one with three values will give you better Gini impurity changes. Or if you look at a continuous feature with an infinite number of values, or let's say n values, that one will be even biased even larger. So that's just sort of a warning. Now for XGBoost, there's several options. There's three options, but one of them shouldn't be considered at all. The two that should be considered are gain and cover. And gain is basically how accuracy changes on average when that feature gets split. And cover is the second derivative of the loss function with respect to that feature. So those are options. You can tell XGBoost to return one or the other. But again, these are not super great metrics. So you'll find people talking about a different approach, which is called permutation importance. And it goes like this. So let's say this works for any model. So it works for XGBoost, random forest, but it works for any model, linear, linear methods, whatever. So what you do is you take a trained model, and for each feature, let's say the first feature, you shuffle all of its values across the training data. So, in your training data, like you have, for sample 1, you have the label in that feature. For sample 2, you have the label in that feature. If I completely randomly permute all those feature entries for that one feature, it becomes useless to predicting the label, right? It's like I've broken all the statistical connections. So essentially what you do is for each feature, you permute it, you randomize it, and you retest that model. And you see how much worse did it get. If it's a really important feature, the model should have gotten a lot worse. That's the idea. You never have to retrain the model. This is for a trained model. It's already trained. You just test it with different permutations. So it's very easy to do. However, it has issues itself. So it's again not perfect. But I want to just emphasize that this is something where the model is already trained. It's not retrained. It's just tested. So a better thing to do, though it's more expensive, is to permute and then retrain, not permute and retest. Actually retrain your model with that permuted feature. Or if you don't want to permute it, just drop it entirely. Just take it out of the model. But that gets us back to what we discussed back in Unit 4, which is that's exactly what you do with stepwise or exhaustive selection. It's just a matter of how you do it. So the moral of the story is that if you really want to do feature selection well, you want to use the methods from Unit 4. Let's say with trees, you can't use lasso with trees, so you're going to have to use like stepwise or exhaustive selection. If you want a quick solution where you don't have to retrain anything, you can use these, and that will give you a rough indication of how important the different features are. Okay, so that's it for this unit. Any questions? Okay, yeah, one question.
Do you not drop and retest just because the model's expecting?
Exactly. Yes. So like I've trained my tree for 10 features. Like if I drop one, like how do I even retest my tree? What do I put in? So that's exactly the reason you have to permute. But down here, like, I don't know if there's any advantage to permuting versus just dropping. I would say this is probably the recommended approach. Okay. All right. Great. So see you guys on Friday then.